V at point A from our previous analysis, right? So from our analysis over here, V at point A is equal to omega L minus 2A over 2. Okay. So now once you have this, right, you write it down. Okay, you write down you write down omega L minus 2A, right, over 2, right? Then the next thing you need to do, so now over here is V as a function of X. So now this is not constant, this is a what? This is an equation. Remember what did I try to teach you before term test 2? How to identify what is a constant, what is an equation. So now you have this as an equation. So you will now have what? You can now write m as a function of X minus by m at point A, right? Minus m at point A, right? Right? Minus m point A. Now you integrate 0 to what? X. Right? So this is omega L minus 2A over 2 dx. So mx is a function of x minus ma. So this is equal to omega, right? L minus 2A over 2x. Because 0, the other point is down here will be minus 0, right? So so we know that moment at point A is equal to 0. So therefore, m as a function of x is equal to omega L minus 2A over 2x. Okay, so you can still use this for what? For non-distributed load. It's still valid mathematically. That's why people that do math, they are very miserable. They have to prove mathematically that this is true, right? So this is x over 2. Okay, then the next one, right? We're going to find when at point A. So at point B.
So wait, Eugene, does this mean that moment is the integration of shear?
Yes, that's it. That's what this is all about. That's what when we started, right? When we started writing this, right? We started with this. Distributed load, you integrate, you get your shear force. Shear force, you integrate, you get your what? Bending moment.
Ah, cool.
We are doing this now. We are doing this all the while. Okay? So at moment at point A, right? Moment at point A, I just show you this because you can also use this for a point load. I want to drive the point that you can also use this for point load. So at point B, when X is equal to A, right? So you can directly substitute. So you substitute. So I'm going to call this equation number. Okay, I'm going to call this equation number. This is my equation number 1. Okay, and then this is my equation number 2. Right. So to find at point B what is going on, right? You're going to substitute X equal to A into equation number 1. Okay, so therefore the shear force at point B, right, is equal to what? Is equal to omega L minus 2A divided by 2 because it's a constant, right? If you look at equation number 1, okay, so you go down here, omega L minus 2A over 2. And then when we go, then at point, we go substitute X is equal to A into equation number 2 now. So you know that your moment at point B is equal to omega L minus 2A multiplied by A divided by 2. Okay, so this will be this will be omega L minus 2A multiplied by 2 divided by 2. And then between point B to C, now point B to C, what can you all see? Can someone tell me? You see a what? A distributed load. Yes or no? So therefore, between point B to point C, right? Between point B to point C, you have A, X, and L minus A. Okay. So now, because we have a distributed load between point B to point C, dV by dx now will be equal to minus omega as a function of x, right? And it's equal to minus omega, yes or no? Right? So when you write this down, it's not equal to 0 now, right? So V from point X minus by VB at point B, this is equal to, you integrate between the limits to L, A to L minus A, omega dx. Okay, so now you have V as a function of X. Now VB we know from the previous point, we know what is our VB is equal to omega L minus 2A over 2, right? So this will be equal to omega X, and omega X is between A, L minus A. Okay, so this will be equal to V as a function of X, right? V as a function of X, and then this will be equal to is equal to omega L minus A minus omega A plus by omega L minus 2A divided by 2. Okay, I'm trying to make sure that I'm okay down here. Okay, so this will become omega L minus by omega A minus by omega A plus by omega L over 2 minus by omega A. Wait, I'm having, wait. I think wait, this is correct. Plus omega L squared over 2 the minus omega A. Did I think the problem, I know where my problem is. Okay, sorry, my bad. This is minus because this is minus omega X, right? So it should be minus. Okay, so my bad. I'm going to rewrite this. Sorry. Don't rush. Minus omega L minus A and A. So B as a function of X is equal to omega L minus 2A over 2 plus by minus omega L minus A plus by omega, because minus will be plus A. So this will be equal to omega L over 2 minus by omega A plus by or minus by omega L plus by omega A plus by omega A. So you can wipe this out, you can wipe that out. So what you will get, hey, sorry, what am I doing? I do apologize. I'm just like, sorry, another boo-boo. I should not be doing this. Too late already. Okay. So is the limits is A to X, okay, not A to L minus A. I do apologize, okay. So this will be equal to, so I bring over, so this will be equal to, so minus omega X, so minus plus by omega A. That's more like it. So omega L over 2 minus by omega A minus by omega X plus by omega A. So this term will be equal to minus omega X, right, plus by omega L divided by 2. Okay, so this function over here is equal to minus omega X, right, plus by omega L over 2. Right, so you can see from here, when you have a distributed load, how it changes now. So the next thing is this, okay? The next thing now, we are going to do, give me another not more than 5 minutes, okay, if I stop making mistake, okay? So the last one that we're going to do is we are going to find a moment. So m as a function of x minus by m at point B, right? So this is equal to a to x, right? And then we know that the equation is minus omega x plus by omega L over 2, okay, dx. Right, we got this from here. We got this, the integration, right? We get the function that I've just written, minus omega x plus by omega L over 2 from here, minus omega x, where I'm going to highlight for you from here. Okay, so now you take that and you integrate. Okay, so that's where I am now. So we're going to integrate. So m as a function of x, we know our mb, right? Our mb is equal to omega L minus 2a multiplied by a divided by 2, right? So this will be equal to minus omega x squared over 2 plus by omega lx over 2. No, omega lx, yeah, x squared over 2, yep. Then the limit is x to a, okay? So m as a function of x is equal to omega L minus 2a divided by multiplied by a divided by 2 plus, so this will be minus omega x squared over 2 plus by omega lx over 2. Then minus will be plus by omega a squared over 2, and then minus by omega la over 2. Okay, then we just expand the term, omega la over 2 minus by omega a squared. Okay, just omega a squared, omega la over 2 omega a squared, then plus by minus omega x squared over 2. Okay, it's all just math now, okay? Plus by omega a squared over 2, and then minus omega la over 2. Okay, so what we can do is we can get rid of these two, right? We can get, and I think that's the only two that we can get rid of. Okay, so in terms of, so you get minus omega x squared over 2 plus by omega lx over 2, right? And then these two you can not cancel, but you can add them up together, is equal to minus omega a squared over 2. Okay, and then when you tidy things up, this will be equal to omega over 2, and then it will be equal to minus x squared plus by lx minus by a squared. Okay, so this is how you use this technique to do what? To deal with point load, and also to deal with distributed load. So I hope y'all will watch the video. I know I'm going quite fast over here, right? I hope you will watch the uploaded video on this. Okay, so this technique that I've discussed can also be used for both point load and distributed load. If that's the case, I'm going to end my lecture over here. Thank you so much. Do apologize that I went over by 15 minutes. Okay, thank you.
Sir, I have a question.
Yes.
Why are the limits a to x?
Because that is between between point B to point C, right?
Right.
So we have not reached point C yet, right?